Hello, my name is Oddgeir Guðmundsson and I welcome you to my presentation, which has the title The Increasing Importance of Holistic End-to-End System Approach when Evaluating Benefits of Energy Efficiency Improvements. First of all, what is the deal with system boundaries and why do they matter? The answer is system boundaries matter because they define the limits of a system. That is, what is considered within the system and what is considered external to it. In principle, the system boundary can range from the primary energy generation and all the way to the end user. A holistic system boundary therefore includes the primary energy system, the thermal energy system, and the final energy consumption. This then opens for the question, what should be included in the system boundary and what can be considered external to it when we are evaluating impact of new solutions in our systems? And the answer is, it depends on the interdependencies between the system elements. In district heating, there are many solutions that have an extended system impact. These solutions can be implemented at different levels of the system and can be both hardware or software based. In this presentation, we will focus on evaluating the benefits from two solutions: more efficient heat exchanger in the energy transfer station, where we will assume a 5 degrees reduction in the return temperature, and then using a software solution for optimizing the supply temperature of the distribution network, where we will assume 5 degrees reduction of the supply temperature. To explore the importance of the system boundary, we will use a reference system which is either using a biomass boiler or a CO2 heat pump. And for the CO2 heat pump, we are assuming that we have 50% renewable power and 50% gas-based power. And those are our baseload plants. And in both cases, the peak load is handled using a natural gas boiler. And in both cases, the baseload plants are dimensioned to cover 60% of the capacity demand, and they will account for 96% of the annual heating demand. And the remaining capacity and heat demand is then coming from the natural gas peak load boiler. Without going into system details, I want to make the following distinction of these two cases. The biomass-based system represents a high temperature source, and the heat pump system then represents a low temperature source. Now, let's get into the more complex part of the presentation, the interdependency of system elements. Now, which system interdependencies should we expect from implementing the considered solution? Commonly for both solutions and considered baseload sources is that identical impact is expected from the distribution network to the end user. The efficiency of the distribution grid will increase, as well as the efficiency of the primary side of the energy transfer station, and then there will be no impact from the secondary side of the energy transfer station to the end user. As for the thermal generation plants, the two solutions will have different upstream impacts. So let's start with the biomass boiler case. In case of a reduced supply temperature, we would expect a marginal, or actually almost no impact on the thermal generation efficiencies, and then only marginal impact on the upstream element from there. And these impacts on the upstream elements are driven by the reduced distribution heat loss. And on the other hand, if we decrease the return temperature, we can assume increased heat recovery from flue gases, which will increase the efficiency of the biomass boiler and consequently avoid some peak load boiler operation. This will change the primary energy mix and consequently lead to a slight difference in the upstream impacts as follows. The primary energy distribution, we would expect a marginal efficiency drop as the natural gas distribution grid is more efficient than biomass distribution. For the primary energy generation, an increased biomass demand will lead to a higher primary energy generation efficiency, as harvesting biomass is more efficient than mining and processing natural gas. Now, as for greenhouse gas emissions, in both cases, we are increasing the system efficiency and therefore the emission will go down. We should expect a larger greenhouse gas emission reduction from reduced return temperature due to increased share of biomass in the primary energy mix. Now, let's explore what changes in the case we have for the low temperature heat source, the CO2 heat pump, as the baseload heat generator. First of all, we should expect the same impact on the distribution network and downstream elements as in the biomass case, and we will therefore focus on the upstream impacts. By lowering the operating temperature of the distribution system, we can significantly increase the operational efficiency of the heat pump. And in this analysis, it's assumed that for every degree reduction in the supply temperature, the efficiency of the heat pump increases by 2%. And for every degree reduction in the return temperature, the efficiency increases by 3%. And this is especially the case for CO2 heat pumps. The increased efficiency of the heat generation will have the following upstream impacts. For the primary energy distribution, we will only expect a marginal efficiency drop, again because the natural gas distribution is so efficient and it's more efficient than the electricity distribution. The efficiency of the primary energy generation will, on the other hand, increase significantly, and that is driven by the greater share of renewable power in the primary energy mix, which is significantly more efficient than the power generation from natural gas. Now, as for the greenhouse gas emissions, the significantly reduced natural gas consumption will lead to significant greenhouse gas emission reductions. Now, let's compare the impact of adopting a traditional silo system boundary against a holistic system boundary when we are evaluating the impact of the different cases, different solutions. If we choose a silo system boundary, we are ignoring both upstream and downstream impacts. That is, we are assuming that a change in one element has no impact on the operation of the other system elements. If we analyze the impact using a silo system boundary, only considering the distribution network, we would expect a similar impact from both solutions if we reduce the return or the supply temperature. And the key impacts for the biomass case are estimated as following. Heat loss savings of approximately 715 megawatt hours per year, a system boundary efficiency increase from 90 to 90.5%, and cost savings of 25,000 euros per year, and greenhouse gas emission reduction of approximately 33 tons CO2 equivalent per year. But what about the heat pump case? Well, as expected, the estimated heat loss savings and system boundary efficiencies are the same. The cost savings are estimated to be 21,000 euro per year, and the greenhouse gas emission reduction about 163 tons CO2 equivalents per year. Now, let's abandon the silo approach and go for the holistic approach. With the holistic approach, we acknowledge that the system elements are interconnected, and that is, a change in one element may lead to a change in the others. So let's move on and look at the impacts. In the analysis for the biomass, it is assumed that the biomass is sustainable, and we will, of course, prioritize biomass over natural gas. And to save time, we will only focus on the differences to the silo approach. So instead of the estimated 750 megawatt hours heat loss savings per year, the holistic focus approach estimates primary energy savings in the range of 1,400 to 2,400 megawatt hours per year. Instead of the estimated savings of 25,000 per year, the holistic focus estimates cost saving from supply temperature reduction to be around 29,000 euros, and if we reduce the return temperature, around 67,000 euros per year. Finally, the greenhouse gas emissions will be estimated to be significantly larger, or a change from 33 tons per year to 450 and 620 tons per year. And this is due to the changed primary energy supply mix. As you might expect, the difference will be more significant in the case of low temperature heat sources, And in the analysis, the renewable power generation is of course prioritized over natural gas-based power generation. So how does the holistic approach compare to the silo approach when we have the low temperature source? Instead of the estimated 715 megawatt-hour heat loss savings per year, the holistic focus estimates primary energy savings in the range of 9,400 to 13,000 megawatt-hours per year. Instead of the estimated saving of 21,000 euros per year, the holistic focus estimates cost savings from supply temperature reduction to be 368,000 euros per year and 518,000 if we are reducing the return temperature. And this is a game-changing difference when we are comparing and choosing what investments we want to make. Finally, the greenhouse gas emissions will be estimated to be significantly larger, a change from 163 tons to 5,800 up to 8,000 tons CO2 equivalent per year. Again, this is because of the changed primary energy supply mix. Now, to conclude, expanded system boundaries highlight higher order benefits, and these higher order benefits can significantly impact investment decisions because we are more accurate when we are estimating the benefits, such as through reduced operating costs due to the reduced heat losses and as well the changed primary energy demands. That can also lead to a reduced future investment demands if we, for example, can get more out of the existing heat plants. A holistic approach will also enable us to better consider the environmental benefits when we are planning for new investments, and by that maximize the future share of renewable in the energy system. So if I try to give a core and clear conclusion, it will be holistic approach enables picking the long-term low-hanging fruit. If you have any questions, you are welcome to contact me using the provided contact details. With this, I thank you for your attention.